You ever just look at the world around you and think, how? You know, how does nature pull off these incredible feats that seem to defy logic? Well, today we're going to dive into a few of those puzzles, things that look impossible on the surface, but are all solved by one of nature's most brilliant and, honestly, kind of secret engineering tricks.
Okay, so let's start with this. Picture a duck just hanging out on a frozen lake. Its body is all warm and toasty under those feathers, but its feet? They're totally bare, standing right on the ice. So how on earth do they not freeze? And maybe even more important, why doesn't all its body heat just pour out through its feet, leaving the poor bird shivering?
And it's not just birds. Let's think about fish. Water has way, way less oxygen than the air we breathe. I mean, we can't survive in it, but fish are doing just fine. They have this ridiculously efficient system for grabbing every last molecule of oxygen, and it's another one of these amazing biological puzzles. And for our last puzzle, we're going to look right inside our own bodies. Deep inside your kidneys, there's a part called the inner medulla. It's super important, but it has a big problem. Proteins are always leaking out of the blood vessels, but there's no lymphatic system, the body's normal cleanup crew, to get rid of them. So how does this area not just get clogged up and, well, fail? So what do a duck's feet, a fish's gills, and a human kidney all have in common? Well, it turns out the answer to all of these questions is exactly the same. It's this beautiful, elegant, and surprisingly simple principle that evolution has just nailed. It's called countercurrent exchange. The whole idea is actually pretty simple when you break it down. You just get two fluids flowing right next to each other, but, and this is the key, in opposite directions. When you do that, you can move stuff between them, like heat or oxygen, with incredible efficiency. It's all about keeping a difference, a gradient between the two along the entire path of contact. And you can really see the magic of it right here. On the left, you've got parallel flow. Everything's moving in the same direction. They swap a little bit, but they even out super fast and then just stop. You're capped at about 50% efficiency. Total waste. But now look at the right, countercurrent flow. Because they're moving in opposite directions, the freshest, most oxygen-rich water is meeting the blood that needs it most. You maintain that gradient the whole way. And the result? We're talking over 80% efficiency. It's a complete game changer. All right, so now that we know the secret, let's go back to our duck on the ice. How is this clever little system keeping that duck's feet from turning into tiny birdsicles? I mean, the challenge is huge, right? Those bare feet are basically radiators, just perfectly designed to dump precious body heat straight into the frozen lake. For a bird trying to survive in the cold, this isn't just a small problem, it's a life or death situation. And here's the solution. It's this incredible piece of biological plumbing you see right here. It's called the retia mirabilia, which is just Latin for wonderful net. And honestly, it is wonderful. It's a tightly packed bundle of arteries and veins. The arteries are carrying warm blood down toward the feet, and the veins are bringing cold blood back up to the body. And since they're flowing in opposite directions, ding, 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 countercurrent. All that heat from the warm arterial blood gets transferred over to the cold venous blood before it even gets to the feet. The heat basically gets recycled, sent right back into the body where it's needed. So by the time the blood actually reaches the foot, it's already cool. And that means almost no heat is lost to the ice. Brilliant. And hey, don't just take my word for it. Here's the proof in the data. This graph shows the temperature of the blood coming back up the leg from the foot. Just follow that line from left to right. Whoa, look at that massive climb. That blood goes from near freezing all the way back up to almost core body temperature in a super short distance. That's the wonderful net in action, recycling heat like a pro. Okay, so let's switch gears. How does this same kind of clever design work in a totally different place, like the kidney? The problem here isn't heat. It's getting rid of waste protein without any of the usual plumbing. And remember, this is a really big deal. If those proteins built up, they would totally mess up the delicate water balance the kidney needs to concentrate urine. It's a critical function. So if there are no lymph vessels to do the cleanup, how does the body solve this puzzle? Well, it uses another beautiful bit of fluid engineering. First, some protein-free fluid flows in and dilutes the whole area. Now, the blood inside the nearby vessels is way more concentrated with protein than the fluid outside. And what does that do? It creates this powerful pulling force. It's called osmosis. It acts like a magnet for water, sucking the dilute fluid and the leaked proteins along for the ride right back into the bloodstream. It's a self-cleaning system that runs on nothing but pressure differences. No extra pipes needed. So when you step back and look at all this, you start to see that these aren't just one-off tricks. This is a fundamental design principle. It's a tool that life has used again and again to solve some of its toughest and most diverse challenges.
When you put it all together, you really see the genius of it. You've got one core concept, countercurrent flow, solving totally different problems. It's saving heat for a bird, grabbing oxygen for a fish, and cleaning up waste in a mammal. It's just one of evolution's absolute masterstrokes, an efficient, low-energy solution that shows up all across the tree of life.
And this quote, right from the scientific paper, just seals the deal. It basically says, yep, we looked, and the blood vessels themselves are doing the cleanup job. It's direct proof of this incredible, hidden biological engineering at work. It really makes you wonder, doesn't it? Once you know to look for something like this, you start seeing these kinds of brilliant designs everywhere. So next time you see a duck on a frozen pond, maybe you'll think about that wonderful net in its legs, and you'll ask yourself, what other invisible engineering marvels are out there, hiding in plain sight, just waiting for us to figure them out?